Hi everyone, welcome to your reading guide for week 5. We're going to talk mostly about human population with a little bit of a nod toward human consumption. And I wanted to start this reading guide off with this sort of tenet that many people in the environmental field believe. And I want to ask you guys whether you believe it now, and then again at the end of the class, do you believe this? So the tenet is there exists no environmental problem that is not in essence a human population problem. And so that basically says that if we didn't have so many millions and billions of people on the planet, we wouldn't have any environmental problems. And you may think that's true or false. I'm curious, and I'll be curious at the end of the class whether your viewpoint on this has changed. In the meantime, let's talk about human population today. So according to Worldometer, the current world population is 7.484 billion people. And the cool thing about Worldometer is that you can basically watch that world population go up as time ticks by. So it gives you births today, births this year, deaths today, deaths this year. You can see there's a whole lot more births happening than there are deaths, which basically explains why our population is indeed growing. Moving this back over to PowerPoint slide. So we estimate that 50 billion people have lived on Earth since our species evolved. That's a huge number of people, but right now we have over 7 billion people on Earth, and that's more than 10% of all the humans that have ever lived on Earth. So we are seeing just a huge increase in the number of humans that have lived on Earth, and this is tied, of course, to some of the things we're seeing as a result of that really large population growth. Okay, so thinking about what this growth has looked like since the Industrial Revolution, which was time early in the 19th century, the 20th century, that basically led to a proliferation of mechanized and automated functions in manufacturing, and allowed people to start having more free time and sort of made it possible to produce goods on a large scale. So we have seen exponential growth basically since about 1,000 years before now. And that's really gotten exponential since that Industrial Revolution begins. So you can see that last little bit of the graph right there just going crazy straight up. So basically when we experience exponential growth, the population is increasing by a constant percent of the population each year. So as the population grows, that constant percent means that more people are added to the population each year, more of a proportion of the population that's existing. So fortunately for us, this percent that characterizes exponential growth is now declining worldwide. So in 1970, we were seeing 2.1% annual growth. Today we're seeing 1.2% annual growth. But as is pretty evident, 1.2% is still enough to add 1 billion people to the planet between 1999 and 2011. 1 billion people. Think about what that means. So I also want to sort of flip this and look a little bit at what's an alternative to that exponential growth. So this curve over here shows exponential growth. The growth rate of the population accelerates through time due to that constant percent of the population being added every year. Probably more likely growth form, which is what we've talked about for most other organisms back in our evolution and population growth chapter in week 4, is that most populations have this carrying capacity, this asymptote here, where the environment will no longer support any additional organisms being added to that particular species population. So logistic growth is sort of an S curve, whereas exponential growth is a J curve. And you can see with logistic growth, the rate accelerates just like in exponential growth, but then it slows down, as we've seen before, as animals start to die due to, or plants or any other organisms start to die due to natural causes and overpopulation and density-dependent effects. And so we assume that at some point this will happen with the human population. We just haven't quite gotten to that yet. Another interesting way to conceptualize population growth is the idea of population doubling times. So this graph just shows you doubling times by region. And then as a definition, doubling time means the number of years for a population to double. So basically you can use this as a way of thinking about the percentage of annual growth. So how fast is a population growing? So if you have a higher percent of annual growth, you're going to have a faster doubling time. So what does this graph show you about the doubling time for Europe versus Africa? You said the doubling time is a lot longer in Europe, and that means that there's a lot lower growth rate. You're absolutely correct. So shorter doubling time, faster growth rate. And just as a little sort of way of figuring out how quickly a population is going to double, you can take the number 70 divided by the exponential growth rate. So for example, our growth rate right now is 1.2%, and that gives us a doubling time of 58 years to double the whole global population. So we are looking at potentially 14 billion people by 2071, if nothing changes with our growth. Now, what do you guys think? Will we just keep growing forever? This is, of course, the big question, right? We're hoping at some point we get to this asymptotic S-curve logistic growth where we level off and experience a carrying capacity for humans, right? And the problem with that is that if we absolutely wait till that moment, potentially, we might run out of food and space. And this was the big concern of Thomas Malthus, who was a British economist back in the early 1800s, and he was looking at population growth in Britain at that time and thought, we are going to run out of food and space. We have to have a carrying capacity. And this has been considered for other societies like the Aztecs, the Mayans, civilizations in the Fertile Crescent, as far as what may have happened to other societies too. And maybe the outcome wasn't exactly that they ran out of food and space, but they may have gotten increasingly aggressive and warlike when they were trying to protect enough resources to feed a growing population. So what we expect to happen is that eventually all countries on our planet will go through what we call the demographic transition. I want to make sure you guys understand this, because this is the key point of this chapter, is really to highlight what the normal stages of demographic growth are for various countries and how they change as we sort of go through the urbanization process. So there are some countries we know that are still developing. There are some that we call developed, like the US. And so in the transition between the developed and the developing countries, we get this change in birth and death rates, which, if you remember from chapter 4, birth and death rates plus some immigration and emigration are really what cause us to experience a certain population growth rate. So if you look at this, we've got stage 1, which is the pre-modern or pre-industrialized stage, and CBR is the birth rate, CDR is the death rate, and then the black line is the total population. So you can see here in stage 1, birth rates and death rates are high. Stage 2 is sort of the early urbanizing, industrializing stage, and that is where we start to see a major decline in the death rate due to increased medical care, better medicines, better child survival, essentially. But it takes a little while for the birth rate to catch up to that, because people still tend to have a lot of kids if they have high child mortality rates, like we did back in stage 1. And so it takes a little while for people to recognize, oh, hey, I don't need to have 12 children because all of them are going to survive to adulthood instead of the 2 that might survive 50 years ago. Stage 3 is this mature industrial stage where the birth rate has finally decreased to sort of catch up with the death rate. And then stage 4, you have the birth rate and the death rate sort of equal to one another again, but you have those rates at much lower levels than they were in the pre-industrial, pre-modern stage. I also want to mention that the age structure of the population is really important to understand. So life expectancy is a major demographic characteristic that we all think of as characterizing a certain population or a certain country. And when we turn it around on humans, we think of life expectancy as being sort of our longevity, right? I expect to live into my 80s. You, if you're 20 now, you may expect to live into your hundreds. People are living longer and longer. as we have better medical care and as we have better resources to put to old age care. Now, it's important to understand what the age structure of a population looks like because it allows you to predict future population growth. So if you look at France here compared to India, you've got fewer people in the 0 to 5 and 5 to 10 age bracket than you do in these working age classes just above them. In contrast, in India, each younger age group has more and more population in it. So what that says is that as these age classes go forward in age in France, at some point there will be more older people than there are younger people. And so that means that population growth will slow because there will be less people having kids. And it also means that there may be a concern over who's going to take care of elderly people. In India, the reverse is true. Population growth here is relatively fixed, at least for the near future, because you have large numbers of young people coming up through the ranks, and they will potentially have more kids and more kids. So until we start to get a decline in the number of young age classes, we probably won't see any decline in population growth rates. You can also see from this that the longevity or life expectancy in India is roughly 70, and the longevity here in France is roughly 85. You can also see that in France, females tend to live a lot longer because the age classes for women are much larger here in later years, versus in India, the life expectancy is not that different between males and females. And a really cool website that I wanted to show you guys really quick is what we call Population Pyramid. And this is super cool in that it enables you to actually visualize this. So if you look at the world population pyramid, or the age structure, this is what it looks like. And in fact, this is kind of cool to see because population growth is not as high down here in the lower age classes as it is in something like India. So that means globally population growth is not as high as it could be. Now if you go to Western Africa, whoa, look at all those kids coming up the ranks, still experiencing high population growth, and we will be for the near future as those kids start to have more kids. And then of course you go to Europe, and we get an even stronger population control process here down in the younger classes, where there's a lot fewer kids being born than there are working class adults. And so population growth here in Europe, you can tell from this graph, has really slowed down. So I'd encourage all of you to play with this fun tool and be able to visualize these age structure graphs. Okay, and then last but not least, I just want to mention a book that your textbook doesn't talk about, which is called The Population Bomb. And if anybody's interested in reading this, it's fantastic reading. It's written quite a long time ago in the 1970s, and the author, Paul Ehrlich, who is a Stanford demographer, warned that if we didn't do something about our population, we were going to see mass starvation of humans in the 1970s and 1980s. And he predicted there were going to be dire consequences of overpopulation on food security and on our environment. Now, he was talking about the 1970s and 1980s, and we really didn't see those predictions come true. And many people have asked at this point, was the population bomb wrong? Have we, in fact, avoided having a major impact on the environment and on our food resources and water resources? And so, really, what I want you guys to think about is that the population bomb was wrong in terms of its timing, but maybe not in terms of its long-term message. Because there are really two components to the human impact on the environment. One is the total population size, and that's what we've been talking about in this chapter mostly. But the second is the consumption, right? The average environmental impact per person in terms of how many resources we're actually using. And this is important because technology and our ability to apply it to all kinds of different aspects of our lives really mitigates the effect of number one. So the green revolution, better and enhanced techniques for making fresh water, like desalinization via reverse osmosis. These technologies can provide food, clean water, and fuel for more and more people. And this is likely why the predictions in the population bomb did not come true in the 1970s and 1980s, because we started increasing our ability to use technology to put it towards solutions for these environmental problems. But technology itself takes resources, right? To build a desalinization plant costs an enormous amount of money, but it also takes land to build it on. It requires access to seawater. It may require a place to dispose of the salt that is removed from the water in reverse osmosis. And so basically technology can increase in some ways our average environmental impact per person in order to provide water for and housing for a greater total population. You're increasing your average environmental impact per person through this use of technology. So that's going to be, I think, our challenge in the future as our population starts to decrease, is understanding how much technology might increase our impact and then how to mitigate that impact. Okay, that's where I'll leave off today. If you have any questions, feel free to get in touch, and I hope you enjoy the rest of this module.